Hello, everyone. So for today's class, I'm going to give some examples and also just to remind you about the concept, and then we'll give some examples about mass transfer. Okay, so if you recall the concept on Wednesday, there is a molecular flux with J, and a small j is for mass flux, and a capital J, A to Z direction is for the molar flux. Okay, so this oil for the flux basis on the stationary reference is N, N for mass flux for the small n, and then capital N for the molar flux. So if you use a molar basis, then you use a capital one. If you use a mass basis, you use just the alphabet small number. Okay, so the basic law or the fixed law is the molecular flux, which are the application of the flux is used based on the stationary reference. And then we need to know the correlation between Na and Ja as well. Okay, so flux is basically the concentration multiplied by the velocity. So the concentration, let's say in a molar one, there would be mass per, for example, per volume, right? And then multiply with the velocity, which is velocity, or if you want to check the unit, the mass is in mass, and the volume would be in the length, so length power of 3. And then for the velocity is distance divided by time, so that would be t, yeah. So this is the time. And then this one is the length. So the mass flux has a unit of the mass divided by length square divided by the t. So yeah, power of to the 1. So for example, the flux shows you the rate of the flux, rate of a mass, which is m over t, mass over time, divide by the area which is L square, or the area square. Okay, or we can say that this velocity, which for this case is the concentration multiplied with number of component per volume. Okay, so if we consider with this definition, Ja equal to rho A, which is the concentration on the mass basis, multiplied with the velocity. This one is the velocity of the component itself, which is the velocity of the absolute one minus the velocity of the medium. And it's also the same velocity of the component one in for this case, multiply with the medium, this one. Okay, so this one, so here then we can say that an A equal to the density multiplied with the velocity. Okay, so the correlation between Na and Ja and Na is defined like this one. So Ja is equal to Na minus the fraction, both in mass or in molar, multiply with Na plus Nb, or this would be the correlation for the mass basis, and this is the correlation for the molar basis. And this is called fixed choose law. So fixed law number 2. Okay, so if you, because we only know the JA, we know the correlation of JA from fixed law for the first one, which is JA equal, or with the Z direction, equal to minus DAB, D, let's say with J, so let's say DCA over B, C, for example. Yeah, so this is the diffusivity, and this is the concentration gradient, and this is the gradient of the distance. So we know JA, but we don't know NB. So if you want to solve the problem, we need to know the correlation between NA and NB. Okay, in three-dimension space, if we consider, for example, Cartesian diagram, Cartesian coordinate, here, for example, for the mass, the JA in a vector equal to the rho or the density, the mass density multiplied with the diffusivity coefficient and multiply with the gradient of the fraction. Or for the molar one, the JA in factor capital 1 equal to minus the concentration of the total of the components, multiply with DAB, and we'll divide with the gradient of the mole fraction. So in the application, similar to the momentum transfer or to the heat transfer, we know there is a distribution concentration of A throughout space where component A move, and the steady state would be influenced by space only because it is not influenced by time. So we can consider there are three types of coordinates. There are rectangular one, which consider the coordinates of x, y, and z, or cylindrical, r, theta, and z, or spherical, r, theta, and psi. And then if you are unsteady, then you add a time dimension, so there would be total of 4 dimensions. So how to solve strategies? The strategy is similar with analogical approach to both momentum balance or to the heat balance. The simplest problem, it is usually steady state, and we consider the transfer only in one direction. So it's like one dimension. And then we also assume that the medium or the fluids is in laminar flow, and the balance is created in space element in a shell. So it will produce a differential equation with the thickness is about delta. Okay, so to solve the solving equation, of course, you need boundary condition. And the boundary condition is typical. Usually the concentration at the surface is known. For example, at R equal to R, capital R at the surface, your concentration A is known. That would be typical, or maybe the surface of the flux is known. For example, at R equal to R, let's say the NA is known. Sometimes there also, if there is a chemical reaction, and the reaction rate also known, because the reaction rate will affect on the K, or the rate of accumulation of the product, or the rate of consumption of the reactant. And then the last one, at the interface between phases, the concentration of the two surfaces is not the same. If you remember about the absorption process, in the absorption process, if you have a gas and a liquid, sometimes the concentration of the gas will decrease, but then it will be equilibrium with the concentration of the liquid like this one. So see, the concentration on the two surface is not the same. So the concentration of the gas and the concentration of the liquid is quite a different one. Okay, so the mass balance, so the laju massa masuk or the mass rate in minus mass rate A out plus production, or maybe consumption or accumulation, something like that, would be equal to 0 in a steady state. It's a steady state, yeah. So here, let's just have a look about the first case. So this first case is about, we have a liquid, the liquid A, let's say, and then the liquid A is situated inside, let's say, glass, like this one, and then like reaction cylinder, tabung reaksi, for example, and then on the top of it, there is a gas stream A and B, which is flowing, okay, which is flowing like this with, let's say, this is X, A, and Z equal to Z2. So it's known, okay? So what happened is, because you have a saturated liquid here and liquid here, and then we have a X over here. So near the liquid, if you think about it, near the liquid, if you have a perfume and then you kind of smell it, really, really near the bottom, you will just smell so many perfume there because this is very, very saturated. This one is quite saturated. So we can assume that XA at Z equal to Z1 is equal to 1. So it is fully saturated with vapor A, which is called equilibrium with the liquid. And over here, the XA is defined because you have A, also, and also B. Because there is a concentration difference, what happens is there would be a mass transfer from the bottom here, from the liquid up to the gas stream. Okay, so the question is, what is correlation between Na and Nb? If you think about it, B is just gas, one gas B. So, and then A is the concentration of this one, of the Na. So if you think about it, Na will transfer, will diffuse to from the liquid A, from over here to Z equal to Z plus 1, Z equal to Z1 into Z equal to Z2. Will diffuse from Z1 to Z2. Because what? Is there any velocity on it? No, there's no velocity. So that means they just diffuse with molecular one. So we have Na, which is to the Z direction. But do we have Nb? In this case, B is only flowing in that direction. So there is no B that's flowing in that direction because there is no fan, there is no, I don't know, compressor or something. So we actually, in this area, there is no B. There is a move. There is no movement of B in the Z direction. So then NB is equal to 0. So if you look at, we go back to the second law of the Fick's law, if you look at over here, back to here, so Na equal to Ja plus Xa plus Na plus Nb. So you can go back there, here, if we, let me write it again, Na equal to Ja plus Xa and A plus Nb. Now we know that, and we have Na, but we don't have Nb. So this, we can say this case is equal to 0. So then you can try to simplify like that. And then we can move this side to the other side to make it easier. Then you can get Ja. So then we can get the correlation between Na and Ja. So Ja over 1 minus Xa. So this is the correlation of the Na and Ja. To solve the problem, of course, you want to start with the shell mass balance, where you want to find there is a mass in, which is the rate in, which is NaZ, multiplied with the area, which is the cross-sectional area, let's say S, minus the NZ out, NaZ out, at, sorry, that's Z plus Z, and then multiply the S, but then there is no production, there is no reaction in here, it's just flowing, so there's no accumulation here. So and divide by 0. So then you can divide it with as delta z, then you end up with d and a over d z equal 0. Now, this NA you can substitute with JA, and JA you can substitute with the Fick's law, which is we know that JA is minus DAB dxa over dz, then you can solve the problem. So this is equation number 1, this is equation number 2, and this is equation number 3. So you can substitute NA with this one, and then JA with that one, and then you will find something with dxa over dz, and then if you do the integration, and then this would be the profile of the concentration. So this is the profile of concentration of XAB, so in here, and then this one is the concentration of XB to with the Z direction. Okay, so this is the case number 1. And then another one, for example, I want you to, I will not give the answer, but here you can find, you can sense if you have a case, this is a pure A, oops, sorry. If this is pure A, and this is pure B, let's say, and then both of them is the same, like 1 mole, or not 1 mole, but like a pure one. So XA is 0 and 1, and XB also 1. And then you open the valve. What happens is A will go to that side, and B will go to that side. So what do you think the correlation with NA and B? Remember, NA is also a vector, and B is also a vector. If you have different direction, then it will be a negative one. So NA would be a positive one. If you have 1 mole over there, you will have 1 mole over there. So that means the rate of NA in a molar one, in the molecule one, would be minus the NB, because NB will go to that way, to the negative one, and then NA go to the positive one. So this is would be your correlation, and then when you substitute to NA, JA plus XA, NA plus NB, you will know what is NA plus NB here, because NA equal to minus NB, then this one equal to 0. So then for this case, if you have two NA and NB together kind of counteract, what happens is you will just kind of delay the effect of velocity, and then your NA is become, oops, NA is now become JA. Okay, last one. I will also ask you as well about the sublimation of a sphere. For example, you have a naphthalene ball, put it in your closet or put in your bathroom, and then within some time, then it is will vaporize, will sublimation in that direction in sphere. So you can have a look. What do you think the if you think that NA is the vapor of the naphthalene ball, and then NB is just the air. So this one is naphthalene ball. So you can think what is the rate, that one. Okay, so the assignment for today, I would like you to find the correlation or the profile of concentration to the direction. What is can you find the profile of the maybe concentration with the direction, with the direction of the R for both three cases. So the profile of the concentration from the mass transfer. Okay, have a look and try it by yourself, and then we'll discuss it next week. Okay, I think that's all from me. Thank you for listening, and then you can see some examples as well from the Birds book, and then it would be helpful as well to try to think to solve the problem. Thank you very much, and I'll see you again next week.